What I'm going to talk about today is nanotechnology. For those of you who had me in CIP, you may be worried that I'm going to give you some really brutal homework assignment. And I might, but what I want you to think about is exceedance probability, because I am hoping, that the consequence of my talk is not extremely large dozing times for you, okay? So the number of people that doze, how long they doze, that's the exceedance probability that I'm in. So I hope that doesn't really happen today. This is kind of an interesting challenge for me, coming up with a nanotechnology talk. I mean, I used to be quite active in nanotechnology. In fact, I was at White House Office of Science and Technology Policy under the Bush administration, right after 9/11. And I was the White House liaison to the National Nanotechnology Initiative. So that's how I got into nanotechnology to begin with. And so it turns out I was thrown into the deep end of the pool, and I had to manage that initiative. I even had to hire the director of the initiative. So I got to know it rather intimately, and I did do some research in that area as well. So the challenging part is doing this at the appropriate level for you. And so this is only going to work if you ask questions. So the way I'm going to do this is I'm going to talk a little bit about the history of nanotechnology and about the things that drive people to do research in it, some of the key findings, and a few key takeaways for you. And then we'll talk a little bit about the implications of that nanotechnology in terms of homeland security, in terms of societal risks. Okay, so this is from Pat Damer, who used to run nanotechnology for the Department of Energy. And this is a really interesting take on what the heck nanotechnology is all about. So, nanotechnology is the physical structures that have scales of nanometers. That's 10 to the minus 9th meters, okay? And so there are a number of things up here. So on the right-hand side of the screen, there are things man-made. And on the left-hand side of the things, there are things that nature makes. And nanotechnology, you've got to remember, a lot of things are driven by what the heck nature has done and how nature does things differently than the way we do things. And so nature is quite capable of assembling and running things at the nanoscale. And by running things, I mean molecular processes, diffusion processes, molecular motors. I want to talk a little bit about that because there's a scale bar, and God only knows if you can even see the scale bar. But the important things for you to look at are, we have an ant on the left-hand side of the screen that's on the order of 5 millimeters in length, and then you show the head of a pin on the right-hand side of the screen. So we're pretty good at making things 5 millimeters, okay? 2 to 5 millimeters. We've gotten better at making things even smaller. But to make a machine the size of an ant is an incredibly challenging thing. And so it is one of those things, though, that inspires you. God, why can't we make machines of that size? Nature does it. How does nature do that? What can we do to mimic what nature is doing? And so you look at a few more things on the left-hand side. The one thing that we can all relate to, well, most of us, is the human hair. 60 to 120 microns in diameter. So that's a length scale that's important. A micron is much larger than a nanometer. But a human hair, just think of it as 100 microns in diameter, okay? And it's scales smaller than that we want to do work on in nanotechnology. So we could stuff 1,000 nanometers in there. We can stuff a lot of things into a human hair. And so when you start to get to those scales, it opens up really interesting possibilities about what you can do. And on the left-hand side, as you continue to go down, you notice that there are blood cells, 7 microns or something like that, red blood cells. Below that, we have a molecular motor, a molecular machine that nature makes to do processing in cells. We have DNA, and on the right-hand side are some of the cool things that people have been doing. And so I'm going to talk a little bit about the cool things that people have been doing to try to match what's going on by nature on the left-hand side. Nature gives us really good examples of what you can do. And so scientists and engineers are trying to figure out, okay, why the heck can't we do those things? And do them in a controlled, repeated manner and get them to do what we want them to do. So that's the important steps that you want to take. So I want to show yet another slide on the scale of things. And so we're down in that range of scales where we're looking at viruses and antibodies. That's the length scale, the size scale that we want to make things. And we want to deliberately make those things and have them do stuff for us. We would love to build a micro machine that could ride around inside your body, like the old movie, right? Fantastic Voyage. So we would like to be able to do that. And there are some things down below that we have made, and I will talk a bit about those things. So anytime you want to ask a question, just go ahead and shout it out. So what inspires all of this is what nature does. Nature does really awesome things. And we are trying to mimic our engineering. David, where are you going? Okay, I was going to reprimand him. I like doing that to him every now and then. Okay, so in the beginning, you see really cool things going on. And some of the cool things you see is on the left-hand side, the foot of a gecko. Now, a gecko can climb up walls. I actually build wall climbing robots. And so I know that that's a cool thing to be able to do. And I'll never forget, there was a DHS guy in my program, and he was responsible for designing the new wall. And I showed my wall climbing robot, and he said, "Ah, shit." So, oh, is this being taped? But he did say that, okay? And then he grabbed me and said, "Wait a second, how much weight can you carry?" I said, "It depends how big you want to make my robot. I can carry a person if you want." Yes, yeah, isn't that lovely? But it's slow. There's the one thing. A gecko is not. So a gecko does something very different. It's very hard for us to be able to build wall climbing robots because a gecko has a really good strength to weight ratio, and it uses very high surface area on the ends of its little digits so that it can exploit what's called van der Waals forces that occur all the time. You're sticking to the chair, not because you're sweating, but we all stick to things, okay? You just don't notice it because the force of adhesion is kind of small. But if you can increase the surface area, you can increase the force of adhesion, and then you can overcome some of the limitations if you can make your machines very light. And so there's large surface area over there, and so that inspired a lot of people. Oh, let's just build wall climbing systems that exploit the same thing that the gecko does. Let's just make really high surface area compliant contacts. And so people have done that. The thing that a gecko can do that is hard for us to do as engineers is it's constantly regenerating the surface. It cleans itself. We are not very good at coming up with schemes for creating high surface area so we get high contact forces, and that the minute we move to the next thing, we got all this crud all over it. You have to clean it before you re-adhere. So that becomes an interesting challenge. So you can do some of it, but to do all of it is very hard to do. On the right-hand side is a picture of a butterfly's wing. Can you believe that structure? Now, I didn't put a scale marker on that, but that is incredibly small stuff. And there's assembly that's going on at the nanoscale in the natural world that occurs all the time. So again, we're inspired by those things. Now, this is something from the 4th century, a cup that is in Rome that had a very interesting phenomenon that they even noticed, okay? Which is if you had a powder of gold inside a liquid and you suspended that gold, if you illuminated the cup from the outside, it was one color. If you illuminated it from the inside, it was another color. And so that just becomes an artistic expression, but it is physics at the nanoscale that's making that happen. It has to do with how light interacts with the particles. And so that's an important phenomenon. At the nanoscale, you get really interesting surface area phenomenon and very interesting interactions with light phenomenon. And so you also get interesting electrical interactions, and I'll talk a little bit about that as well. This is the Damascus Sword, and it turns out when they do a chemical analysis on the Damascus Sword, there's something, it's been known in steels for a really long time that the way you process them, fold them, hammer them, all of that, locks in a microstructure that you can't see with the naked eye. You have to look at it under a microscope, and in fact, very high magnification microscopes, to see that there's a really super fine layered structure inside that material. And that super fine collection of layers is responsible for the very high strength that you get out of these things. And they found that when they looked at it using what's called a transmission electron microscope, so transmission electron microscope shoots electrons through something. Electrons have both particle and wave properties. So we can do optics using electrons just like we can with light. You just have to focus it and use lenses in a different way. The cool thing is, because you're passing them through this structure, you get really, really high resolution images from them. And they found when they looked at the Damascus Sword, this is more recent of course, they didn't know that when they made the sword, they found there's carbon nanotubes inside of it. Nanoscale structures inside the steel. So that ends up becoming an interesting thing. Now, it gave it unique properties. It was better than other swords of the time, but they didn't really know why. They just know I have to make it in this way. So they were incredible craftsmen and artisans who would make that stuff. Okay, then Faraday. God, Faraday did all. There's some people that just do so much stuff, it's ridiculous. Again, Faraday found that if you put gold particles, very fine gold particles, it's yellow, you put it in a solution and it's red. You know, so those sorts of things make people wonder what the heck is going on. Well, how is it interacting with the outside physical world that's changing the color of the system? And so it takes a long time to sort all of that stuff out. Now I want to change directions a little bit. I want to change, so there's all sorts of cool things, phenomena on the nanoscale that people were exploiting, but they didn't know they were exploiting it. Now that we have new scientific stools, oh geez. I must have been to the vet the other day. No, now that we have new tools, we can understand mechanistically what's going on, and then we can deliberately make it to improve the properties, in fact, okay? So people have always been interested in building machines to do things for them, and I'm just showing some calculating machines here. And calculating machines, of course, were important for commerce. It is really nice to be able to figure out how much of something you have, if you charge this much for it, how much money you're going to make, all of that sort of stuff. So it drives the development of technologies, which went from the abacus to the Babbage, the slide rule's later than the Babbage machine, but to build calculating machines. And those calculating machines were also important when you start to think about, you know, we're going to siege the castle and we want a loft burning things at it. And we'd really like to know how hard we have to throw those things so they'll make it inside the castle walls. Ooh, a wall, okay. So they make it inside the castle walls and start a fire. So you need to understand the equations of motion of that stuff, and you need to be able to solve it, okay? So you want a machine. You actually want a machine that you use on site to do that calculation for you, so that you can accurately hit what you're trying to hit, right? So warfare drove a lot of technology, right? So the calculating machines, though, moved away from the mechanical, which were incredibly ingenious machines, and they moved towards the electronics world. Then we had a huge revolution when John Bardeen invented the transistor when he was at Bell Labs. John Bardeen won 3 Nobel Prizes. He was a remarkable individual. This is just one of them. Invented the transistor, which allowed people to reliably control the flow of current through a circuit and use the magnitudes of those things to do calculations. Right? So at that point, we weren't ready for it. And then came Jack Kilby, and Jack Kilby said, geez, we can invent the microprocessor. We can take this stuff, scale these transistors down, and put them on a silicon wafer. In order to do that, they had to figure out how to put stuff on a silicon wafer. They had to figure out how you could put metal conductors in it, and also how you could etch the silicon to create regions of known properties. So that was a huge deal. That is a huge breakthrough. And why were they doing it? They were doing it because they wanted to do electronic calculations. Okay? So you're going to notice something here, and that is, not only do they want to make it work, they also want to make it smaller. So making things smaller allows you to get more processing power in it. You look at your phones now, they're phenomenal. They're phenomenal in how much you can store in your phones. How many thousands of photographs do you have in your phones? It's not that long ago that we couldn't do that. We didn't have the storage capacity because we didn't have the information density to make things small enough for us to be able to do it. So making it smaller makes a huge difference. So Kilby did that, and then Gordon Moore, who was the CEO of Intel, sort of figured out, God, you know, there's this thing going on, and every few years we double the density of chips we can put in a given area. And so computers that used to take up a full room would take up a desktop, would take up a phone. So making things smaller allowed you to do more. So there's a huge drive to make things smaller. All right? And then Fineman came before what we just talked about, but Fineman said something rather interesting. And Richard Fineman is considered the father of nanotechnology in the following sense. He gave a talk at Caltech where he said there's plenty of room at the bottom. He talked about, because he's a high energy physicist, he was trying to figure out what is the structure of matter at the subatomic scale. And when you work on those scales, you realize how much stuff there is down there. The number of atoms that just make this up is ginormous, right? And so he said, if there's some way we can take information and write it at a smaller scale, we could put all of the Library of Congress, all the information in the Library of Congress in a 1 centimeter cube. And so he challenged people to do that. He was a great thinker. He didn't do that sort of stuff, but he challenged others to do it. There's plenty of room at the bottom is the key talk that was given, and you can actually watch it. Caltech has it. It's pretty amazing stuff. Fineman was just outrageously smart. Okay, so nano isn't new. It's actually not new at all. It's been going on for a long time. Nature's been doing it for a long time. But as our scientific tools developed, we began to be able to see things at a very small scale, and we began to manipulate things in a very small scale. And I show the electronics stuff because the electronics industry was enabling for nanotechnology. Absolutely. Gordon Moore's notion of let's just make it smaller and smaller and smaller and smaller and smaller reached a point where they realized, hey, you know, the wavelength of light that we're using to pattern our silicon wafers, we've now reached the limit of the wavelength of light. We can't make them any smaller. How are we going to make them smaller? We have to come up with a different way of making the structures. And so, following Fineman's talk, a lot of people said, gee, you know, what we could do is we could actually use little nanomachines to make dimples, sort of like punch cards. I don't know how many have been around long enough, but punch cards of code on a very, very small scale. And they realized, hey, you know, we could actually increase the information density going that route. So the push to make it smaller, driven by microelectronics industry, is important, okay? So the fact that nature has been doing nano and we're just chasing nature's tail, what's important is you got to see what the heck is happening. So you have to develop scientific tools to be able to do it. So you have to have the tools before you can do the engineering. And so you need the basic science to build the tools then help you do the engineering. So you got to be able to see what's happening. You have to be able to manipulate things at the nanoscale, and then deliberately make things at the nanoscale. Okay? So is all of this making some sort of sense to you? And so what happened, there's sort of a convergence of this physical stuff and the electronic stuff. And microelectronics industry really enabled it. Okay, so during the Clinton administration, they set up the National Nanotechnology Initiative. It was originally run by Tom Khalil, and it included a number of basic agencies to come together to fund research in nanotechnology. And that funding would go to tools development, basic science, and engineering development. All right, so it grew quite a bit. And what I'm showing here is a plot of the funding that occurred as part of the National Nanotechnology Initiative. It peaked a while ago, and it's sort of dropped and is sort of holding steady right now. Okay, so there's funding available. It's a huge initiative. It's an important initiative. Okay, we can debate that in a little bit, but I mentioned that in order for us to do this, we got to be able to see things at the nanoscale. And so money through the NNI supported the development of a novel transmission electron aberration-corrected microscope at Berkeley. And they were able, for the first time, can you see the red on the red? That is a single sheet of what's called graphene. All of that little hexagonal structure has carbon atoms, okay? And they form these carbon rings, and it's a single atomic layer thick. So Berkeley developed a microscope that allowed them to image in high resolution single atoms thick layers of graphene. Okay, so first thing, we got to be able to image it. The other thing over here on the rightmost side, so this is 2 nanometers, this little marker bar here. This gold particle is on the order of 2 nanometers across. It is a gold nanoparticle embedded in some other metallic matrix. And you can see the individual atoms in the nanoparticle, which is cool, okay? To see, you can count them. You can actually count how many atoms are in there. This is doing what Fineman wanted them to do, okay? So they developed tools to be able to see things. That's first most important step. I don't know, look, I'm not gonna do this, but in 1981, Binning and Rohrer at IBM Zurich developed what's called the scanning tunneling electron microscope, which was designed to image, again, single atoms. And what they did is they hover a probe over a surface, and they have to get close enough to that surface. So can you imagine how hard this is to do, right? You have to approach a surface and get within a single atomic radius of that surface. And then you move it across the surface, and you apply a voltage, and you get what's called a tunneling current, which is quantum mechanical effect. And you can measure the magnitude of that current and use that to image the atoms that are underneath the probe. And so you can create 3-dimensional maps. It was a huge breakthrough, again. It takes a lot of time to do things like that, a lot of effort, and let's just face it, a lot of money to do it, okay? So those kind of breakthroughs are expensive, but they end up transforming things, okay? Following the scanning tunneling microscope, which only worked on conductive and semiconductor materials, people developed the atomic force microscope. Now, the atomic force microscope is a direct outcome of what the microelectronics industry was doing, okay? So microelectronics industry figured out how to pattern and make shapes out of silicon. Then people came along and said, gee, you know, let's exploit the manufacturing process of microelectronics to make really, really small beams, okay? So they make beams that are not in a nanometer range, but that are about 10 microns across, 1 micron thick, 100 microns long. So this is a really fine beam, okay? It's smaller than a human hair. All right? Now, if you take that beam, which you can make using microelectronic processing, you simply etch it out of silicon. If you take that beam and you put a little tip on it and you drag it across something, it will respond to the profile of the stuff underneath it. It's called a profilometer. That's really all it is. You measure the deflection of the end of it using a laser, and it allows you to figure out what the heck the 3-dimensional topology is of what you're dragging the AFM across. Okay? Now, you might not think that's so important, But again, you got to be able to see stuff in order to understand what the heck is going on. You're making something, and then you image it. You say, okay, here's what I think I made, here's what I actually made. So those things are important. The other thing is, once you realize you can do that, then you realize, gosh, maybe we could use this to push things around. So if we can image on the nanoscale, maybe we can use it to push some stuff around, and if we can push some stuff around, maybe we can build structures out of it. Now, you can imagine that if you're building things that are really puny, using really puny devices, you're going to build something really puny, okay? And it's going to take a really long time, all right? So that's what fundamental science is about. And then people get a hold of it and say, gee, I want to be able to make things like that in mass production setting at a price that everyone can afford, okay, in a process that I can repeat. Not some scientist in Zurich going like this, okay? That isn't going to work. You're not going to get high productivity that way. And this, by the way, this bloody cantilever beam ends up being the basis for chemical sensors that have been developed since that time. All right, so the fundamental research, and gee, we got to be able to see this stuff. How are we going to see it? Let's build a cantilever profilometer using microelectronic routes, and then somebody goes, hey, if we can build cantilever profilometers, we can do some other cool stuff as well. So I'll get to that in a moment, all right? This is another interesting thing. This was the Bucky Ball, discovered by Rick Smalley's group out of Rice University. I got to tell you, the cool thing about running the nanotechnology initiative from the White House when I did is that I got to meet all these cool people, like Rick Smalley. He was awesome. He's a really great guy. He discovered the Bucky Ball. And what is the Bucky Ball? So you can tell that Smalley's a geek because he named it after our Buckminster Fuller. That's this guy over here who built those dome structures. Everyone's seen those dome structures. They're mostly on playgrounds, I gotta say. But our Buckminster Fuller wrote a book called Operating Manuals for Spaceship Earth. He's like one of the first early green engineers, okay? And Rick Smalley liked him a lot, so when they saw this structure, these are all carbon atoms, and they assemble themselves into something that looks like a soccer ball. And when they saw that thing, he said, oh, that looks just like one of Buckminster Fuller's designs, so they called it a Bucky Ball. All right, so they needed to see it. Now, you might think, who cares? Right? I mean, honestly, right? Who cares? Okay, so I saw a teeny-weeny soccer ball stuck inside a material under a microscope. Whoa. But if you have a teeny-weeny soccer ball stuck inside a material somewhere, you can sort of say, hey, maybe we can build a molecular cage and put something inside it, and we can carry the stuff inside it to a location where we want that stuff to be delivered. So you could create a chemical bomb for cancer treatment. If you can figure out how to get it in there and how to functionalize the exterior of it so that it goes to a specific location, okay? So you gotta let people dream, and when they find stuff like this, you pat them on the back and say, keep doing it, Rick, right? So it may seem crazy. But then guess what? IBM people, Egler and Schweitzer at IBM Alumni Research said, hey, geez, we can actually move atoms around. Those are single atoms, okay? They manipulated single atoms into position and wrote IBM. Now, it didn't save IBM. But it was an important demonstration, okay, of, hey, we can manipulate stuff on the atomic scale, and we can put it where we want it to be. So that means we can deliberately locate it. So we can deliberately force it to have a certain structure, okay? The problem with that deliberate forcing, again, is, as you can imagine, you don't make cars that way. You don't say, geez, how many atoms do we need to make a car? Let's just start putting them together. You never get there. Right. I mean, I know you're laughing, but you know, there's sort of an absurdity in some way. You do the basic science, and then you got to figure out, well, we want to make structures, but we got to figure out how to mass produce them. And so the manufacturing at the nanoscale is a really important part of the discovery. And there are manufacturing centers that are associated with it that enable researchers to do research where they have access to all sorts of really cool tools. Okay, so this is, again, an interesting example of making things. So in 1999, Wilson Ho and I don't know how to pronounce the name, Lee, they assembled a molecule. They assembled a molecule. They moved the constituents around, and so if you go from A, B, C, D, what you find is they ended up creating this iron cobalt molecule. You'll see it down there at the bottom, by bringing the constituents together. So they found that you could, not using standard chemical processes, but using a combination of direct manipulation of the atoms and their chemical predispositions, create things, right? So that's kind of a huge breakthrough. Again, it's not to scale, so you certainly don't have a Dow Chemical saying, hey, let's create chemicals this way. You don't do it that way. Then Chad Mackin came up with this idea of doing something called Dippen Nano lithography. What is Dippen Nano lithography? It is that cantilever beam again. It's basically like a writing quill, okay? And you create a bunch of writing quills, and you use the writing quills to write a pattern on surfaces, all right? So it allows you to create really, really tiny scale electrical conductors or whatever, lots of things you can imagine making that way. All right, so it was a bit of a breakthrough again, and I think what you're finding, I think, if you look at this, there's a lot of sort of old school ideas behind it, right? And we're just going to push things around. We're going to assemble things by pushing them around. So now, look at this 500 micron structure to the left over here. This is from Sandia National Laboratories. That thing has a bunch of, what do we have? 1, 2, 3, 4, 5, 6, something like 8 cantilever beams. Those are very, very small. That little black line up there, of the left side of the leftmost image, 500 microns. Those are very tiny cantilever beams. And so when you can create an array of cantilever beams like that, what you can do is you can functionalize them, which is what the image on the right is saying. And in this particular case, this is when a lot of people were very interested in using microcantilever beams to detect this prostate-specific antigen for prostate cancer. So medical diagnostics, chemical sensing is what this is all about. You functionalize the beam with stuff that will only latch on to specific known antigens. And so you can create, if you can create an array with thousands of beams, you can functionalize each of them differently, and you can create chemical sensors from that sort of thing. All right? So it's an interesting combination. This stuff, the Sandia image on the leftmost side is manufactured using microelectronics methodologies. It's made out of silicon. Then they do some manipulations of things that are on the nanoscale, and they can detect stuff that's on the nanoscale. Okay, can we build a machine that's small enough? Can it make its way around inside the bloodstream? Can it be functionalized with sensors like this to detect specific proteins? And the answer to all of that, the answer is yes. Can we do it? Yet no. Okay? So there's going to be an interesting, we'll talk about that. You know, get the body to do things for you versus let's build machines to do those things, right? That's the interesting thing that's going on. I mean, once you start to do this biomimicry, and if you can, like CRISPR does, hijack genetic control, then you may be able to just build these machines, have the body build the machines for you, right? Instead of spending all this time making the machines, because your body does it all the time anyway. It produces blood cells, it produces cells, it's always making stuff. It's always involved in nano manufacture. So I don't know where that's going to go. I don't know which is going to win out. all right, in that sense. Okay, so there's another thing. I mean, look, once you have this idea of cantilever beams, you can't put a laser. If you want to detect the deflection, what you have to do is you build that cantilever beam into a microelectronic substrate. That's the upper right image. And as it deflects, it changes the conductivity of the substrate. So you can measure deflection through a change in the current that's passing through. So that sort of enables the kind of thing that Kurzweil was talking about, all right? And there's lots of science to back that stuff up. All right, now what is so important about the nanoscale is that making things smaller ends up, they behave differently. That's what's so interesting about it. Now, so smaller is different. So you have all this large stuff, and you have a history, a database of mechanical properties and electrical properties, and then you start making things smaller, and you find, hey, wait, they don't behave like that anymore. So the first key takeaway here is smaller is different, okay? And the important thing is what happens when you start to make things small is their surface area. See, this is like an exceedance plot. Do you guys see? It's not. It's just a power law, but it looks like an exceedance plot. All I did was this is the ratio of area to volume, okay? And so as you make things smaller, the surface area to volume ratio, right, increases. And so surface effects become more important. Okay, so surface area to volume ratio increases. Surface effects become more important to those things. That is why a gecko can climb up a wall, surface area stuff, okay? So it behaves differently. This gentleman, I had the pleasure of meeting him as well, Jacob Israelishvili, just died recently. He invented this whole field of surface forces. And I was in his lab once, and he was telling me about this really cool experiment that he did. I can't find the publication, but he did this experiment. He was taking gold nanoparticles, and he built a machine to measure the force of interaction between them. And so what happens, these are plots that show sort of, if you go from right to left, you see that little valley in there. It has to do, as you bring things together, they don't notice each other, then all of a sudden they want to pull together, okay? And so he was measuring all those surface forces to try to get a handle on the surface force effect as you make things really small. And he found that there was a length scale, a size scale for the gold nanoparticles. When he took 2 gold nanoparticles of a certain size scale, below which this always happened, and he brought them together, instead of them just glomming together, they would come together and then form a new, larger gold particle. So they behaved like liquids. At a certain size scale, they behave not like solids, but like liquids. So that's an interesting phenomenon, okay, that Jacob explored, and is a really interesting thing. So it's telling you that as you make things small, the fundamental physics that's guiding their behavior and interaction, it's still the same fundamental physics, but different forces, different processes become more important. Now, so again, I want to ask this, who cares? Who cares if we can do all of this stuff? It's enabling is what it is. It enables other breakthroughs, and sometimes you don't have any idea what's going to come of it. I guarantee you, when they were first studying nuclear magnetic resonance, they had no idea that MRI would become a fundamental part of medicine. Nuclear magnetic resonance in the early days sounded like absolute, who cares? We're going to look at the spin up and spin down and subatomic levels. I mean, who cares about this stuff? And then they found they could exploit it to do imaging. So this is the other thing that's happening here. So I mentioned that as you make it smaller, you get really large surface areas. And so you can exploit large surface areas. One way you can exploit large surface areas is in the catalytic converters of your vehicles. You have to do chemistry. This gas is flowing across an area, and you want to catalyze a chemical reaction. The larger the surface area, the more catalysis you get. And so they have exploited high surface area particles to enhance catalysis. So the chemical industry does this, right? They use high surface area exploitation to do it. But high surface area is also really important in batteries. As we move from fossil fuels to more sustainable stuff, as we move from fossil fuel, gasoline, diesel vehicles to electric vehicles, we need better batteries. We just do, okay? And one way you build better batteries is by making the electrodes at the ends of higher surface area. Because the current that can flow through a battery depends upon the surface area of the electrodes. The other thing is, when you discharge, you're changing the surface area. When you recharge, you're rebuilding that surface area. You want to be able to discharge and recharge and maintain that surface area structure. So nanotechnology is fundamental to chemistry and batteries. Batteries is just electrochemistry. Okay, so they're sort of the same basic idea. So using nanoscale particles to fabricate the electrodes changes the power density you can get out of a battery. That's an important thing. Okay. So Jennifer Lewis at Harvard is making, I can't even read that from here. The little white marker bar is 200 microns. Look at the electrode, the battery that Jennifer Lewis has made using nano-assembly methodologies. That's a pretty small battery. Okay? So smaller stuff, higher energy density. We're going to get into all that in a moment. So all this to make it smaller, okay? All of this stuff to make it smaller is done for a very specific reason. If you think about all of the electronics you have, you can jam more information in less volume. So you can put more stuff in there. So you can keep pictures that you don't really want for a really long time of people you're no longer interested in. So, right? So there you go. You got that going for you. The other thing is that I didn't show you this yet, but when you make these things smaller, they actually get stronger. And that was the driver behind composite materials. Composite materials came about because they found that as you make things smaller, as you move from big structures to smaller diameter structures, the strength of those structures went up. And so smaller was stronger until you reach size scales where other weird stuff happens. So not only can you get higher information density, you get what's called higher specific strengths. With the batteries, you can store more energy in less volume. Because it's smaller, it takes less energy to run it, right? So smaller, lighter, faster, cheaper. That's the tough part, cheaper. All that stuff it creates efficiencies. And so there's a huge desire to move to smaller, faster, lighter, all right? Those are the things, smaller, faster, lighter. That drives a lot of this, all right? Right, so I just want to show you that smaller is stronger by taking a look at a couple of charts here. There's two things that I'm looking at. This is glass fiber strength as a function of diameter. So as we bring the diameter down, the strength of the fibers goes up rather dramatically. Again, it's a power law for all of those you have in my class. They show up everywhere. We see the same thing with carbon nanotubes, which I haven't talked about just yet. I'll show you an image of a carbon nanotube in a minute. All right? So smaller is stronger, okay? Smaller is lighter. We can get more information density. We can increase the strength. Those are all drivers for this sort of stuff. And this smaller is stronger. Wait, we made composite materials with that understanding. We understood that the fibers were stronger. And so we make things with fiber reinforced. This isn't even at the nanoscale, but now we can start doing stuff with nanotube reinforcement. So it becomes enablers for advanced technologies. In this case, they absorb radar energy instead of sending it back, or they deflect it, and that's a much, much lighter package. So make it lighter. So new materials, making it lighter, all right? So it's not just electronics, it's materials, biomarkers, molecular motors. All of this stuff is driven by this desire to make it smaller, okay? So this is a carbon nanotube. They discovered, you saw, I mentioned that there was carbon nanotubes in the Damascus Sword, okay? I mean, for the longest time, people didn't realize they were all over the place. We didn't even know it. You don't realize that for the longest time, we were trying to make synthetic diamond. I mean, people were trying to get rich off of synthetic diamond. Then they find that every time a jet flies, it's producing synthetic diamond. It's just really, really tiny particles. Right? So these are interesting things that occur. It's almost like nature's doing this stuff all the time. We figure it out, and then we figure out how to reproduce it at scales that matter to us. So carbon nanotube, when I showed you the Bucky Ball, it was that soccer ball of carbon atoms. The carbon nanotube is instead a pill-shaped device, okay, that has closed ends, okay? So those are incredibly strong bonds. Carbon nanotubes are really strong. So making things at that scale and making them at lengths so that you can exploit the strength of them is really, really useful. But they found another funky thing with carbon nanotubes. And that is, if you take this carbon nanotube and you just trim all the bonds along the length of it, and you just move them by 1 atomic bond spacing, it changes from a conductor to a semiconductor. The electrical properties change. Okay? You move it 2, it changes again. You move it again, it changes back. I mean, so that is called chirality, how it spins. The bonds spin as you're coming down. It's called chirality. And you can change the electrical properties by controlling the chirality. So why does that interest anybody? Holy crap, we can make microelectronics out of this stuff. Not only that, they're really strong. So we could make really strong new composite materials that have embedded microelectronics in them so that we could do constant health monitoring of structures made from these things. So it enables a lot of stuff. Does this make any sense to you? So cool properties happening here. But then you can make nanochinos. So I'll never forget. Look, I got to tell you, when we were working on the NNI, it was like, can we have any good applications out there of what anybody's actually doing and making money off of? And nanochinos was one of the best things we could come up with. So what do they have? They have a cool property of repelling water. So you have some nanoparticles embedded into the fabric, and they're really hydrophobic, and so they repel water. All right, so you can wear your nanochinos to the coffee drive-through, spill the coffee, and not stain them. So that's a huge nano breakthrough. Okay. Right, I know it sounds crazy. Targeted drug delivery, man. Targeted drug delivery. This is the idea behind that Bucky Ball that I was mentioning to you, although this is not the Bucky Ball. This is a bigger thing. And so the idea here is that you create a chemical, let's just call it a chemical bomb, okay, that is carried by some nanoparticle that has little functional proteins on the outside that bond with specific docking sites on specific tissues. Okay? And if you can get it to do that and then release its payload, you can actually do targeted chemotherapy and deliver the chemo only at the site of the cancer. Okay? They've already done things like this, and they've really done a great job on contrast enhancements. So one of the things that's kind of important is when you're doing imaging, you want to make sure you know where the cancer cells are. And so they can functionalize gold nanoparticles so that they will bond with specific sites on cancer cells. And because those gold particles go there, they enhance the contrast image when you do MRI. And so you can get a really good idea of where all the cancer is using contrast image enhancement. That is happening, and that is working, all right? So that's a definite benefit. The other thing that this nanotechnology is enabling is flexible electronics. It's really kind of important because silicon is not a flexible material. And we would like to be able to put electronics in many locations where it has to move around, okay, and flex. So this nano is enabling flexible electronics as well. So the challenge to all of this stuff is how do we exploit the property of the small in a marketplace of big things? We get these unique properties out of small stuff, but how do we use it in products? How do we deploy it in everyday products that everybody can use? So we want to be able to use these things. And so I want to talk briefly about the way we make stuff. I just want to show you what the issues are here. We manufacture by removal processes for the most part, okay? We start with big chunks of stuff and we machine it down to the shape we want, okay? That's a materials removal manufacturing process. We are now also doing something called additive manufacture, where instead of removing materials, we build a part up. So we leave material only where we need it, instead of starting with a big chunk of something and turning it down. We just build it up. So additive manufacturing is much more like what they want to do with nano, okay? So we're going to get to the Homeland, and of course, guided self-assembly. Nature does something pretty phenomenal. The code to make all of the systems is written into the original cells. So Nano would like to do something like that, guided self-assembly. And so they are doing it, okay? So you can create, look, we aren't doing it in a huge way just yet, but on the left-hand side over there, you find that you put a bunch of molecules into a solution, and if you decorate the molecules with the right sort of chemicals at the tips of them, when you dry the solution, all the molecules stand up and they create an ordered array. So it's called guided self-assembly. We want to do the same thing with these spherical assemblies. I'll show you one of those in a second. So they do guided self-assembly for drug delivery already, okay? They just create molecules that want to attract each other and want to repel each other, and then in solution they assemble themselves in a very specific way and create these really cool spheres, all right? So we know how to do that sort of stuff. Guided self-assembly. Engines of Creation was written by Drexler as his thesis for MIT, and that was him saying, geez, what we need to do is make little nano robots that make replicas of themselves. And then they just would make more and more and more and more and more and more. Right off the bat, when you make small stuff, you can run into what I'll call the asbestos problem, and that is you have stuff that's just the right size that gets lodged in your body. Okay, so you got to be really careful about that. The toxicity just from physical lodging, and your body launches an immune response to it, overreacts, you get these cytokine storms, and you die, which is not good. So you got to be careful about just the natural toxicity that can occur with certain of these things. Gold is no big deal, but you don't want to fill yourself up with gold anyway. So you got to be careful about how you manage all of these small nanoparticles. They want to do self-assembly, but you have to worry, of course, about hijacking the self-assembly process in some way or another. And instead of it doing what you want it to do, it does something else, okay? So the other thing when you have self-assembly is it can hybridize and you don't know what the consequences would be. Other thing I want to talk about is CRISPR. Everyone knows about CRISPR right now for gene editing. CRISPR has all the best intentions in the world. Let's fix where we have genetic defects. But now we have a system that can go in and snip your DNA and replace segments of it with something else. That's an interesting process that can have unintended consequences. And that's a nanoscale process, okay? It's nature's nanoscale, but it is a nanoscale process. I want to talk about the rise of Chinese science, okay? Because I think the biggest threat to Homeland Security is who's going to own the technology. This is really important. China has changed dramatically the technology and knowledge landscape, okay, of the entire knowledge and scientific enterprise. If you look on the left graph over here, we show China in red, okay, and we have the United States in green, and you see that in terms of publications on nanotechnology. Now, I'm not trying to say that they're all great, okay? But nonetheless, the absolute number of publications, they have surpassed us now. They're doing more than we are, all right? And I've been around long enough to remember, I went to school with Chinese grad students. When I went to school, every Chinese grad student wanted to stay in America. They go where the opportunity is now. And China is aggressively courting them all to come back. So get educated, go home, develop the engineering and science there. That is a huge, huge threat to our scientific enterprise. The other thing you'll see there is the rise in Chinese, you can't see the rise, but Chinese funding is approaching what we do in funding nanotechnology. So it takes money to do this stuff, and China's starting to put more and more money into it. So that's an interesting threat. Just the other things that are showing up are patent applications and granted patents. The Chinese have passed us on both of those now. All right? So there is a huge security implication just in terms of who's going to own the technology. Do you want to be a first-rate power with first-rate science and technology that actually leads the world? Or are you willing to cede that leadership in science and technology to a rival? And you can decide whether or not the rival is a serious one. I think this is a serious threat to our science and technology enterprise. All right, probably the biggest one. And it cuts across domains. It's not just nanotechnology. The last paper there is just the last chart on the right-hand side is just how many publications are coming out of China now. Enormous numbers of publications coming out of China. They are beginning to really challenge us in a domain that we have owned since World War II. We have been the science and technology education and research destination for the world, and China is beginning to challenge that. They aren't yet getting a lot of students from other countries, okay? But they're getting more. And that would be the next thing, because we have been on the good side of the brain drain. We have taken really smart people from all over the world and had them come here and develop science and technology for us here that helped our industry lead. So that's a huge deal. So, okay, so I took it in that direction, okay? In terms of the threat posed by a rival power. So the summary of all of this stuff is that engineering at the small scale gives unique opportunities, okay, for materials, medicines, electronics, period. In order to make this work, we need new methods of manufacture that do a better job mimicking what nature does. And that means guided self-assembly in some way or another. Otherwise, we can't scale it properly. We know that increased component density enables advancements in all areas of technology, period. More information, more efficiency, higher energy density, it resonates across the board. And nano, the next thing is nano is a key enabler for artificial intelligence and autonomous systems, which are the other big area of incredible interest and concern. So artificial intelligence, smaller, faster, lighter, will completely change the threat space, okay? So what I originally wanted to do was do this and then have you talk about some of the threats that you see could be arising. Think creatively, okay? That's all I want to do, so I want to engage you in your thoughts now, all right? Thank you. If you design something to do self-assembly, self-assembly is a little bit different than self-replication, but nonetheless, if it's taking raw materials and making something else out of those raw materials, whether they be proteins or anything, you run the risk of, wasn't that Cat's Cradle by Kurt Vonnegut also? Ice 9 taking over the world? I mean, you do run the risk of unintended consequences. I think it's a legit thing to think about. And so look, people are working on ideas of sort of installing self-destructive bombs inside the thing, so it can only do it so many times before it can't do it any longer. So legitimate concern. I don't know what to say about how you deal with it. So these are interesting problems because people are doing nanotech, okay? It's the same thing with cloning, and it's the same thing with CRISPR. You saw the Chinese scientists who did the genetic manipulation on humans, right? So that they would be resistant to HIV, right? So it's an interesting problem of how do you contain it? What you want more than anything is that all the participants are ethical, right? And I don't know how to guarantee that all the participants will be ethical, especially if they see huge payoff somewhere. I can make a gazillion bucks doing this sort of thing. It's, I don't know what to say, right? Right? It's almost like the war to end all wars. Dynamite, it would be so destructive, no one would ever do it again, right? No one would ever use these weapons. Right. I share the same concerns, actually. So interestingly, though, when I mentioned China, so do you decide, okay, wait, we're just going to compete with them in discovery? Do we just charge forward and do discovery? Or do we have some parameters of agreement on domains that we would carefully constrain so that it doesn't get ahead of us? I mean, I think you could look at genetically modified organisms already, and GMOs and non-GMOs, right? I mean, the cat's out of the bag, man. You can't have a GMO field next to a non-GMO field. There's cross-pollination. So, right, does it get away from you? I think if you wanted my short answer, I would say it always does. If you're not an expert in it, you can still go to some of the overview talks that are available in lots of different areas and look at what is emerging and think about the effects that any sort of emerging thing might have on you in your domain. So, if I were talking to a bunch of firefighters, for instance, I would say things like, nanotechnology could well pave the way towards new high-temperature resistant materials that make it safer for you to do your job responding to fire emergencies, okay? And the technologies that emerge, DARPA funded a big program recently, but I'm sorry if I'm going astray, but I'm just trying to say what you try to look for is you say, what are the things that are coming that could help me in my profession? And if I attend these conferences and talk to the program managers, maybe by talking to the program managers, I can say, gee, we really have a need in this area. Why don't you fund some programs in that area? And see if you can find some common ground that still would drive the fundamental science, but help address a need that you happen to have in your particular area. There's a lot of research in that particular area of energy harvesting is the way it's described. And so is there energy that's available that I can harvest and use to power myself? So a perfectly good example of energy harvesting would be putting sensors on an aircraft that takes advantage of the vibrations in the wings. So anytime, if something is vibrating, then you can build a little energy harvesting mechanism that converts that vibrational energy directly into electricity that can be used to power the system. So you're basically a parasite on an energy source from someplace else. So you take that vibrational energy, you convert it into electricity. Then the other thing is thermoelectricity, which has been used in the space program for a long time. If there's a temperature difference that you can exploit, so this works really well. Again, energy harvesting for low power consumption systems, which micro and nano systems would be. If there's a temperature difference that you can exploit, you get a current flow related to that temperature difference. And even though it's not enough for stuff at our scale for us to use, small machines can use that sort of thing. And then you can embed solar cells directly into systems. And they can exploit the direct conversion of the solar cells, or they can simply exploit the heat that's being generated on them when sun shines on them. The only challenging part about that is that those kinds of energy harvesting systems only work when that energy source is available. And so oftentimes you might want them to work when that's not available, so then you got to build a battery storage system for it as well. And that takes, that takes space and weight and volume. So does it help answer your question? Okay. Energy harvesting is a real deal. People use it all the time. In fact, athletic shoes, put stuff in your shoes to harvest the impact energies of your foot strikes. All that stuff is real. When it comes to the carbon sequestration, there are a lot of real active research programs that is, in essence, artificial photosynthesis to take and capture CO2 and bind it in some way, okay, into carbohydrates or something else like that. So that's legit. There are people that are doing it already. The problem is it's not efficient enough yet. But there was a Dutch group that just released some work just last week that is apparently kind of a breakthrough. I haven't had a chance to read it, but that is legit. But I would worry that I don't want it to make us inactive, in other words. I mean, we can't always wait for technology to save us. Sometimes we have to save ourselves before the technology becomes available. But I do think that this whole notion of artificial photosynthesis and carbon sequestration in a novel, unique way, enabled by nanotechnology catalysis, is legit. Okay, that's real. That's definitely something people are looking into, and I would predict that it is going to happen. I just don't know if it'll happen on a large scale. You introduce micro machines and you change the way bad actors can act. I mean, that's absolutely true. I mean, autonomous vehicles does that as well, right? I mean, you just hijack the control system and drive the person off of a bridge somewhere. These technologies can definitely be used with bad intentions to achieve goals that are not aligned with what our goals may be. I mean, you are right. You start to make this stuff at a small scale, and it can be introduced without people knowing it. Just like now, by the way, you could be getting a cold, right? I mean, we're talking about making things on the scale of viruses, and that means that you could breathe them in, and they could do things to you. I mean, I think that's true. I think building a really complex machine at that scale would be hard, but just a bad, look, man, there are bad natural actors that we can exploit already anyway, okay? So I do think that, I think building the machines to do that is kind of tricky, but CRISPR to me is much more potentially bad player than these nano machines, because that's CRISPR's happening, man. Nano machines are still a dream. We aren't making things the size of ants that crawl around, okay? Although some people are trying right now, okay? I hear what you're saying. I definitely agree that all technology can be used to do bad things, and you can't necessarily see it. So, better put your aluminum over your head and wrap yourself in cellophane. No, sorry. No, I don't know what to say. I mean, you're right. Bad things could be done with it. I agree. We're in a really interesting political climate where addressing those things seems to, instead of having a conversation, we just peeve people off. So in my class, I talk about not all regulations are bad. There are regulations that can impede progress, and there are regulations that are designed for the general good of people. And so how you identify which is which, when people try to tie you in knots about that, is a challenging problem in and of itself. And there's always the issue of, industry is always saying, hey, leave us alone, stop regulating us, we know how to run perfectly in the marketplace. And those industries generally have a fair amount of financial clout, and so because of that, they get disproportionate political clout, is what I would say, right? So money buys you clout. So if that's how you want me to, I don't know how else to address it other than that, in a way. So if you can dangle the prospect of job creation or job destruction, then you can drive and influence the policy playing field in ways that, because everybody wants to create new jobs and no one wants to eliminate old jobs. But which brings me to, so I don't know how to do what you're saying. How do we react quickly? Well, usually we react quickly when there's a disaster, right? Then all of a sudden it's unfettered and things get done. The more deliberate actions seem to be much, much, much harder to take because they don't seem to be urgent. And whenever things don't seem to be urgent, then people will discuss them ad nauseum, right? I got in trouble at the NSF because I said industry was basically ceding responsibility to the government, forcing the government to fund all of the research and development, and then they would exploit and take advantage of it. I got in big trouble for saying that. I was deliberately being provocative, but so they have relied on our higher education system and the brain drain immigration pipeline to fuel their industries, intellectual capital. There's no doubt about it. So I don't know what they are doing now. I know that they are worried about whether or not they're going to be able to fill the needs. And certainly Silicon Valley, which is near here, worries a lot about that because it's very much an intellectual enterprise, not a manufacturing enterprise in any way. And so they're worried about where they're going to get the intellectual talent to fill their needs into the future. And they've come up with all these weird creative schemes of ships offshore where foreign nationals could live and bizarre stuff like that to overcome immigration hurdles and green card hurdles. So what they can do directly, though, is sponsor green cards, right? Other than that, I don't know. I mean, and of course, try to influence policy decisions. Those are the two things that industry could do. They could also sponsor research activities, right? They could sponsor educational activities to get more people in the pipeline earlier on so that we would do a better job, perhaps, educating our own, right? Instead of looking abroad for it.